Okay, we're continuing on where we left off last time. So we stopped right there. I want to talk about what a position vector is. A position vector, its initial point is always at the origin. So if I'm given 2 points x and y, so 2 points A and B, in which each has its own coordinates. If I want to find a position vector, I would simply take x2 minus x1, assuming I'm running A to B, and y2 minus y1. And the vector would look like the I component and the j component, just for reference, in case you're not comfortable with those. They call this the I-axis and they call this the j-axis. So, if I'm looking at a vector, if I have vector 2i minus j, that means move 2 to the right and 1 down. And there it is. That's the vector they're talking about. You could write this using component notation, 2 for the I, negative 1 for the j. A position vector, you guys, is very close to our standard angle. Remember how we drew the angles first, and you could be anywhere? And to make all the angles standard, in which we all have the same sketch, if we were to do 35 degrees, we all start on the positive x-axis. Rotation counterclockwise was positive, clockwise was negative. Here we're doing the same, and I'll show you with examples what that means in a minute. Once I label a couple of examples, I'll show you. So directions on 29 through 36. The vector v has initial point P and terminal point Q. So we start at P and end at Q. This is the vector PQ. And if I put a grid right there, where should I put it? Yeah, let me put it there. If I put a grid right there, and I'll try and P is at the origin. Okay, well, again, that's what we're trying to do. I'll tell you in a minute. P is at the origin, we're right there. And Q is at negative 3, negative 5. Okay. We call this a standard vector because you're starting at the origin. So we could see clearly what this is doing. I'm using a color, different colors. So we could see that this is shifting 3 units to the left and 5 units down from the origin. Now, a standard vector, let me go back up there. A position vector, I'm sorry, not standard vector. A position vector, its initial point is always at the origin. What if I'm looking at problem number, let me see which one. I think I picked 32 or 34. It doesn't matter which one. There we go. So what if I'm looking at this vector? This is like me saying sketch a graph of 40 degrees without setting where to start, and you could say, oh, this is 45 degrees. And you're right, that's before we made it standard. Now if I want a position vector, well, first let me show you what this is. PQ, you're starting at negative 3, negative 1, negative 2, negative 3, 2. That's B. And you're terminating at 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Your vector is really right there. This is a vector. What we do, we say, you know what? If I want this point to be at the origin, how would that look like? Well, think about it. You're moving 1, 2, 3, 4, 5, 6, 7, 8, 9 to the right. So 1, 2, 3, 4, 5, 6, 7, 8, 9 to the right. And you moved how many units up? You moved 1, 2, 3, actually 1, 2, what, 3 up. 1, 2, 3 up. Right? Pretty much, if I look at what happened, you moved 9 to the right and 3 up. And do you see that if I start at the origin, moving 9 to the right and 3 up, will end up terminating right there? So whatever this vector PQ does, this vector PQ does. It shifts anything 9 units to the right, 3 units up. This one does that. So, picking a vector, as long as you maintain its magnitude and its direction with the horizontal, as long as you maintain the same magnitude and the angle that it makes with the horizontal, it's fine, they're the same. How do you do that algebraically? Well, we say end minus beginning will always work. The vector PQ will be, you take the end minus the beginning, comma, that's the I component, and you take the end minus the beginning, always end minus beginning, and vector PQ in standard, they don't call it standard, they call it position. The position vector of PQ is really 9, 3, which means if instead of doing what this is asking, if you start at the origin and move 9 in the I direction, which is the X, and 3 in the J, which is the Y, guess what? You'll end up being the same place. Another way of thinking about this, another way, this is something that I saw. If you know that you need movement in this direction, this is where you want to drop off the baggage, and this is where you want to pick it up. So let's say this is something new that you're inventing. Well, if you make it in standard position, you know exactly how many units you need to move to the right and how many units you need to move to the up or down. And that's how it is. And that's what this formula is for. This formula right there says, if you were given, I cluttered those. If you were given point A and point B, and you want to figure out the vector from A to B, take end minus beginning, x2 minus x1, that's this, y2 minus y1, that's this, or it's right there. We're going to do one more just to make sure that we're seeing this, and let me pick another problem. So let me see which one. I'm thinking maybe all of them are the same. Let's go with 34, I suppose. And again, I'm going to show you what we did. And the reason I'm showing you that, I need you to understand how these vectors, position vectors, are crafted so that when we get to the applications, everything makes sense. So P is at negative 1, 4. 1, 2, 3, 4. This is P. Q is at 1, 2, 3, 4, 5, 6, 1, 2. So do we see that this vector actually, so I know it goes down and I know it moves to the right, but I'm not sure by how many. Well, guess what? No need to worry. I could count, or I could say end minus beginning and end minus beginning. And I could say that is 7, negative 2. So this is claiming that you're going to move 2 down. It's claiming this is 2 down and 7 to the right. Well, I could count, right? Isn't that 1, 2? And isn't that 1, 2, 3, 4, 5, 6, 7? Well, to really get this starting at the origin, I will move 1, 2, 3, 4, 5, 6, 7, and 2 down. And that is the equivalent of that vector PQ, but starting at the origin. And that's what we want. We want all of these to start at the origin. Alright, so as long as with respect to the x-axis, the angle is the same, and the length, which is the magnitude of this vector, is the same, we say those are equivalent or equal for us at this stage, will be fine. Now, we want to talk about a couple of more things. There are a few more things to define on any vectors, and one of them, how to find the length. And this is going to go back to R and theta, you guys. Third time will be a charm in case you didn't see it. If I go in and I look at, wrong one. Come on, wasting time. Time we don't have. All right. The magnitude. The magnitude is really nothing more than our r. And they denote it by absolute value or double absolute value, depending on which author you're using, is the length, literally r, of the vector. And the direction, again, I'm using colors that are hard to see. And the direction, can you guess what the direction is? It's theta. But here they make theta always positive. And since you're using an absolute value on the magnitude, r is always positive. So, in vector land, magnitude is always positive, which is r, and direction, which is theta, is always positive. It can be negative. So if I was given v to be x and y, the magnitude is the square root of x squared plus y squared. That's like me saying r squared equal x squared plus y squared. And guess what? Tan of theta equal b over a. So b theta will equal the inverse tangent of b over a. So this is the third time we're doing this. And let's start playing with this a bit. Hopefully reviewing, reinforcing what we already know. And I want to look at the next set of problems. And, oh boy, this is in the way. Let me just move this just a bit. There we go. Oh, it's going to offset everything. That's okay. If I go ahead and use in problems 37 through 59, find the magnitude. That's r. That's nothing more than a fancy way of putting r. Instead of r, which, becomes dull after a while, probably this is more sophisticated. So if I take, let's say, problem number 38. So if they gave me the vector, that means this vector is in not standard position. This is a position vector. Meaning what? Meaning I'm going to start at the origin. I'm going to move 5 back. 1, 2, 3, 4, 5. And 12 down. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I am right here. If I draw a line running from the origin, does that look familiar? Except here it has direction. Well, that's like r and theta. Right? Well, if this is -5 and this, oh, I'm sorry. Oh boy, this is embarrassing. Okay, just for time, let's say this said -12. I'll do another one. I'm sorry. I just can't go back and edit this, and I don't want to redo the whole video. So, if I was to ask you, hey, how do you find this magnitude of v? Isn't that our traditional r? And wouldn't you say r squared equals what? -5 squared plus a -12 squared? And r would be the square root of 25 plus 144, 169, 13. Normally it's plus or minus. In vector land, that can't happen. And it seems I have time to do maybe one more before I go on to the next video. So let me go ahead and pick another problem. And if I pick problem number 39 is tradition. Let's look at 40. We did 40 over and over. And I'm going to add to it. We have about a minute, which is plenty of time. You can do a lot in 1 minute. And what's the key in all of these sections? 4-1, 4-3, and 4-4. Plot it. How hard is it to plot one of those? So, isn't this actually -1, -1? If I move 1 left, 1 down, guess what? The magnitude of v, well, I already know that's radical 2. And I'm going to add to it. Can you tell me the direction? Tan of theta equals 1 over 1. And I'm finding the reference angle for like the 50th time. Reference angle will be pi over 4. And what is pi over 4 in the fourth quadrant? Theta would be 5 pi over 4. Or 225 degrees. There we go. Didn't ask for theta yet, but I thought I'll find it just for the heck of it.